Hello everyone. Today, my group are going to discuss a critical pillar of modern automotive engineering, which is the material selection. So, when we design a vehicle, the materials we chose are the foundation for everything else, from how the car handles to how it protects the passenger. Our goal is to achieve high torsional rigidity and crash worthiness while keeping the vehicle's mass to an absolute minimum. Our group members consist of me, myself, Melvin Ryan, Faris Hafizuddin, Wan Muhammad Shafwan, and Hanif Irfan. As of the introduction of this project, choosing the right material is the most important thing in automotive industry. In automotive engineering, material choice isn't just a detail, it is the foundation. It dictates how a car performs on the road, how it protects its occupant during car crash, as well as how it affects the manufacturing cost. For the goal of the structural design, when we design structural vehicle, we are chasing three goals simultaneously, which are the high torsional rigidity, top tier crash worthiness, and minimum mass. By achieving all three of these goals, it is the key to the maximum energy efficiency. For the limitation of the traditional metals, steels and aluminum were in the industry standards because they are predictable and easy to manufacture in high volumes. However, we are now hitting the physical constraints of conventional metallurgy. So, to meet new environmental regulations, we need a better strength to weight ratio than the traditional metals could provide. Last but not least, the shift to the advanced composite materials. So the future of automotive lies in advanced composite materials, specifically fiber reinforced polymers. This material gives us the best of both worlds, which allows us to cut component weight while maintaining the structural rigidity as well as the safety that we expect from steel. One of the problems that comes in today's automotive industry is that the constraints of the traditional metal used to produce the vehicles. So most vehicles today are made using traditional stamping of steel and aluminum. While these are easy to mass produce, their high density is a major problem. We are reaching a point where the metallic materials can no longer help the industry comply with strict new carbon emission laws because they make vehicles unnecessarily heavy, leading to higher energy consumption as well as the operational costs. Next, for the EV challenge, the stakes are even higher. Conventional materials are simply no longer adequate in an EV or electric vehicle. The kilogram of weight loss is directly proportional to the battery range. So to make EVs viable for the mass market, we must move away from the heavy alloy as and toward lighter alternatives. For the technical barrier of the composites like carbon fiber and glass fiber are anisotropic, which means that their strength changes based on direction. This causes it harder to simulate and can lead to dangerous failures like determination or brittle. And last but not least is the manufacturing and the cost hurdles. Beyond the engineering challenges, the raw materials are expensive, and the long manufacturing cycle times make them even more difficult to use in high volume production. For this project, the first objective is to choose and analyze the appropriate lightweight composite material, which we have chosen to use carbon fiber reinforced polymers as well as the glass fiber reinforced polymers according to their weight to strength ratio, as well as the application in the automotive structure. Next is to examine the production step of the chosen automotive composites. via resin transfer molding, or known as RTM, procedure to ascertain the production of the intricate geometries. And last but not least is to test the mechanical performance and the structural integrity of the composite material that we have chosen, along with the standardized tension and impact testing to verify that the composites in the automotive safety is crashworthiness standards. The scope of our material selection is very specific. We are focusing on carbon fiber and glass fiber reinforced polymers. For the matrix, the glue that holds the fiber, we are using epoxy and polypropylene as the major matrix materials. This allows us to compare how different reinforcement behave with different resin systems. Next, for manufacturing, we have restricted our scope to the resin transfer molding method. We are not just going to make flat plates, we are more focusing on the geometry of critical automotive parts like bumper, beams, and B pillars. We have set a thickness range of 3 mm to 10 mm to ensure that we maintain the perfect balance between weight reduction and structural strength. And last but not least, is our mechanical verification is governed by international standards. We are using ASTM D3039 for tensile testing to find the ultimate strength and Young's modulus, and ASTM D6110 for Charpy impact testing. This last part is crucial because it will tell us the energy absorption capacity, which is essential on how much impact the part can take before it fails.
Okay, so for the first part, for our literature review is, as you can see, the first topic is automotive lightweighting and composite. So the points here is, from what we get from our literature review is, first, the lightweighting is a key strategy in modern automotive engineering to improve fuel efficiency and reduce environmental impact. This is especially important for electric vehicles or EVs, where reducing weight directly increases battery range. Instead of traditional metal, composite materials are increasingly used because they can significantly reduce vehicle weight while maintaining structural performance. And the second point is FRP composites, which means CFRP and JFRP. Okay, so FRP composites actually consists of strong fibers embedded in a polymer matrix. Carbon fiber composites provide an excellent mechanical performance but are expensive and much difficult to recycle. Glass fiber composites, however, offer a better balance between performance and cost, making them more practical for large-scale automotive applications. So, last but not least, point 3, manufacturing and mechanical performance. Okay, resin transfer molding or RTM is a key manufacturing method for automotive composite because it allows high quality parts with complex geometries. FRP composites shows high strength and good impact energy absorption, which is essential for crash safety. Standard tensile and impact tests are used to confirm that these materials meet automotive performance requirements.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shafran bin Azman. Okay, I will continue to explain about the methodology. Before that, I'm recording using my phone. So, because my camera laptop have issue on their camera on. Okay, we start with this project aims to make a test and glass fiber composite using resin transfer molding to see if it's suitable for lightweight car parts. The lightweight material are crucial for improving fuel efficiency. This composite is a cost-effective option that provides good strength. Okay, from the picture you can see there's a figure 3.1 that I take from report, project report, flowchart of the experimental methodology. Okay, started with material selection and preform prep, and go to the manufacturing via RTM and testing and characteristic, and also data analysis and evaluation. Okay, next we go to the next stage. We go to the material selection and specimen selection. You can see a schematic of the specimen there and electrode setting. B is schematic of PARTM process, and C photograph of the experimental setup. So we will start with the material selection. We have 20 plies of carbon fiber were stacked, each measuring 500 mm in width, 1000 mm in length, and 0.25 mm in thickness. The fibers in both the wave direction were T300B 3K plain woven carbon fibers. The numbers of rod and wave thread were 51 ends, 10 cm and 51 peaks per cm respectively. And we added the epoxy resin had a viscosity of 450 MPa at 25 Celsius and specific gravity of 1.11 gml at 25 Celsius in the anchored state. So there's a layer by layer. We can see the flow media, and it also have a release film, Teflon, preform, and sealant tape, and the important thing is the glass mold to cover the layer of each of the specimen of electrode. We continue to the next slide. This is also same to the previous slide, which is this one is for a scale effect of the fibermetric interface in sheet molding compound application, which is we can find in automotive parts, especially in automotive manufacturing part. Okay, there's 4 stages. Okay, for the first stage of the characterization consists of qualitative observation during the compounding and molding process for each glass fiber type. Among the points of comparison is the assessment of sheet density and wetting in charge, as well as non-destructive analysis of any imperfection observed after molding. So we go next for the second stage, that include micro scale testing to quantify and differences in single fiber tensile properties, such as surface morphology and single fiber interfacial shear strength, that might resulting for chemical sizing packages in different class of the products. Okay, we go for the third stage, evaluated the macro scale quasi-static properties for each glass fiber sizing, formulation using tensile, flexural in plane shear, and compression properties of model panels. Okay, we go for the last stage, which is the fourth stage, which is investigate mesoscale sources of variance related to localized effect of fiber volume fraction and fiber orientation distribution as inferred from SCT and 3D DIC. We can see, if you refer to the picture, we have SMC lift gate 1 meter micromechanics, and we go to the SMC charge stack 100 cm and single SMC charge 20 cm, which is have a fiber bundles inside the layer. And then lastly is fibermetric interface. Fibermetric must be in 50 micromechanics, which is micrometer. This is the last of the part of the methodology. We have the mechanical testing protocol. The pictures, the figures show the experimental mechanical testing setup for tensile, flexural, short, beam strength, in plane shear, and compression based on ASTM standard. So it have their own standard on this testing. So we need to follow what they need when you're doing the testing, mechanical testing. So tensile tests will be performed according to ASTM D3039 using a 100 kilonewton instron 5982 universal testing machine that equipped in hydraulic wedge grips and 50 astrosometer. It have a minimum to 5 specimen will be tested at a displacement rate of 2 millimeter per minute, and data for ultimate tensile strength UTS, Young modulus E, and failure strength will be recorded and be analyzed. So it have a failure mode will be photographed and categorized, such as fiber breakage and delamination. You have a low velocity impact also. You have a testing like a flexural testing, which is focused on 3-point band. Flexural properties will be determined per ASTM D790 to simulate bending loads common in panels. Test will be conducted at a span to depth ratio of 32 1 at a crosshead speed of 1 mm per minute.
Assalamualaikum, my name is Muhammad Hanif Irfan. Now moving for the section 4.0, I will discuss the finding of our project focusing on the material selection, mechanical performance and the manufacturing feasibility. First, let's discuss for our why we choose a glass fiber reinforced polymer GFRP. In the automotive industry, we always face a trade-off. Traditionally, steel is cheap but very heavy. On the other hand, carbon fiber CFRP is extremely light and strong, but the material cost is too high for mass market cars. So our study found out that GFRP offer the optimal balance. Although its absolute strength is lower than steel, it is its specific strength, which is the strength to weight ratio, is excellent. This makes it the viable candidate for structural parts where reducing weight is the critical. Okay, now let's take a look at the mechanical data. Please refer to this figure. This stress strain curve tell us exactly how our material behave. From our tensile test, we achieve an ultimate tensile strength UTS of 285 megapascal and a stiffness or Young modulus of approximately 18 GPa. So, which mean gigapascal. If you look at the line, it is perfectly straight up to the breaking point. This indicates linear elastic behavior, unlike steel, which stretch and bends, or plastic deformation. Our GFRP sample is brittle. It hold it hold the load rigidly until it reach 1.58% strain and then fail abruptly. This rigidity is actually good for exterior panel to prevent fluttering. Now regarding the manufacturing process, we use resin transfer molding RTM because it provides the high surface quality needed for automotive body panels. The most critical factor we analyzed was resin viscosity. We use an epoxy with a low viscosity of under 500 cp. Why is this important? Because our woven fiber preform is very dense. The resin needs to be thin enough to flow into every gap. If the viscosity is too high, we get dry spot or voids, which weakens the part Therefore, controlling the flow is the key to structural integrity. Now, regarding the manufacturing process, we use resin transfer molding (RTM) because it provides the high surface quality needed for automotive body panels. The most critical factor we analyzed was resin viscosity. We use an epoxy with a low viscosity of under 500 cp. Why is this important? Because our woven fiber preform is very dense. The resin needs to be thin enough to flow into every gap. If the viscosity is too high, we get dry spot or voids, which weakens the part. Therefore, controlling the flow is the key to structural integrity.